Good day, Doctor. I'm Vanessa, and today we'll be presenting on our fuzzy logic group assignment. My teammates are Jonathan, Xin Jie, and Xin Cao. This is our presentation outline. We will start with introduction and problem statement, followed by the objective and design of the fuzzy logic system, and we conclude by system testing. Let's start with the introduction. University students often struggle to decide whether they should attend class, especially when feeling tired, overwhelmed, or dealing with bad weather. Skipping classes may seem harmless short term, but it often affects understanding, participation, and grade outcomes. A student typically considers whether to go to a class on the following factors, such as how tired they are, whether the class content is important, how close exams are, whether the weather is bad, and how much additional travel effort is required to go to the class. This decision-making process is not black and white, but involves subjective uncertainty, thus making it an excellent real-life scenario for a fuzzy logic system. Continuing with the objective of the fuzzy logic system, the primary objective is to develop a fuzzy decision support system, or in short, DSS, to help students make a smart and balanced decision on attending class by evaluating multiple uncertain real-life factors including personal condition such as sleep or fatigue, academic context, environmental conditions such as the weather. The system is designed to process multiple crisp inputs and produce a single definite crisp recommendation score that is flexible and realistic for student life. Next, I'll pass to Jonathan for the system design. Continuing.
For the student attendance problem, we have implemented the Mamdani fuzzy model. This selection is based on its primary technical advantage in human-centric decision-making, which helps produce acceptable, definite outputs from ambiguous or inaccurate human-like inputs. Furthermore, the Mamdani model provides linguistic intuition by allowing for linguistic terms in both the antecedents and the consequent. This approach is more effective for an adversary system than the mathematical functions found in Sugeno models because it mirrors natural human reasoning. The system translates subjective student conditions into 5 distinct linguistic variables. We've identified 4 inputs, also known as antecedents: sleep level, topic importance, exam proximity, and weather level. Our single output, or consequent, is the attendance recommendation. To ensure consistency across the system, we utilize a standardized 0 to 10 scale for most variables, while exam proximity is measured over a 30-day universe of discourse to reflect a realistic academic timeline. In our practical implementation, using the Scikit fuzzy library, we began by defining the resolution of our universe of discourse. As shown in the code for task 4a, we used control.antecedent and control.consequent to initialize our linguistic variables. We utilized numpy.arrange to establish the numerical range for each variable, such as defining sleep from 0 to 11 with a step of 1. This step is critical as it provides the crisp numerical foundation required for the subsequent fuzzification process. Fuzzification is the technical process of transforming crisp values into membership grades corresponding to fuzzy sets. To maintain system stability, we limited each variable to 2 or 3 membership functions. This is a crucial design choice because too many functions can cause rapid rule firing and an unstable system, while too few may ignore small input changes. We also strictly followed the 25 to 50% overlap rule, ensuring that neighboring fuzzy sets overlap sufficiently to allow for smooth transitions in the final recommendation output. Finally, for task 4b, we programmed a hybrid of triangular and trapezoidal membership functions. We use trapezoidal membership functions such as first.trapmf for the sleep low set to provide a stable plateau or maximum membership at extreme values where a condition is considered critical. Conversely, we applied triangular membership functions using fast.try.mf for transitional terms like sleep medium to establish a distinct point of maximum truth. Our output recommendation uses symmetrical sets to ensure unbiased decision making throughout the inference process.
Alright, so proceed with our knowledge-based design. We have implemented it using the fuzzy rule-based system where we follow the linguistic if-then structure that represent the human-like reasoning in attendance decision, such as if a student is really tired, they are less likely to attend, and if the topic is important or there is an upcoming exam, they are more likely to attend, and also bad weather might keep them away unless the class is very important. So each rule links a combination of student-related condition to an attendance recommendation such as skip, optional, and attend. So this allows multiple factors to jointly influence the outcome instead of relying on the hard threshold. So over here you can see that we have defined a total of 8 rules for our knowledge base. So all these rules provide a comprehensive logical coverage so that our system can produce meaningful outputs for any valid combination of input values. So next is our inference engine, where it processes our fuzzy inputs and return a fuzzy output. So it comprises of 3 different layers. The first one is a rule evaluation, in which CRIPS inputs are converted into the membership values and evaluated against the knowledge base. So when multiple antecedents exist, the minimum T norm is used for the logical AND operation, following the generalized modus ponens principle. Then we aggregate the rule output, so each rule produces a fuzzy output set after the evaluation. And since multiple rules may lead to the same recommendation category, we aggregate these outputs using the maximum operator. And finally, the aggregated result forms a single fuzzy membership function representing the overall recommendation, which will then be passed to the declassification stage. Alright, so this is how we actually implement our inference engine and also our knowledge base. So on top, you can see that we actually have a control system under the attendance clip that will actually holds all our rules in our knowledge base. And we also have the attendance sim, which is a control system simulation, which is the runtime engine that will execute our fuzzy system later. And next is our rule definition. So for each rule, we have 2 variables. The first one is the antecedents and the second one is the consequence. So for each rule, as we have multiple antecedents, we connect them using the AND symbol representing the T norm. Then for our consequence, we directly put the output as defined in the earlier stage. And lastly, we have the attendance sim.input to receive all the input values from the user, and then we execute it using the attendance sim.compute. So this compute will actually perform all the fuzzy reasoning steps automatically, starting from the fuzzification of the CRIPS input, rule evaluation, aggregation using max operator, and then lastly is the defuzzification using the centroid as default.
After the fuzzy inference process, the system output is still in a fuzzy form. To obtain a final numerical result, we apply defuzzification using the central method. This method converts an aggregate fuzzy output into a single crisp value by considering the entire output distribution. It's chosen because it produces smooth and stable results, which are stable for decision-making system. After obtaining the crisp value, we further map it into a human-readable decision category: skip, optional, or attend. After the fuzzy inference, to evaluate the effectiveness of our fuzzy logic system, we test it using predefined test cases. Each test case consists of crisp input values that represent realistic student scenarios. The system processes these inputs through fuzzy inference and defuzzification, and the resulting crisp output are then mapped to final decision categories for easier interpretation. Here is a summary of our test result. In the second test case, the overall conditions are moderate, leading to an optional decision. In the third test case, the student is well rested and the exam is approaching, so the system recommends attend. This result align well with intuitive human decision making. The screenshot below also showing example of interactive testing, where we can observe the system's real-time behavior under different input conditions. Here is a sum. In conclusion, our fuzzy logic system effectively handles uncertainty in student attendance decision. The system produces consistent and human-like recommendation based on multiple real-life factors. Overall, the testing result confirms the practicality and effectiveness of the proposed model. In conclusion, that's all about our fuzzy logic system project. Thank you for your listening. That's all about